we have started discussing about various types of faults in the last class, and we discussed energy system transients, and we have discussed three different kinds of transient: ultra fast, medium, and slow transients. Ultra fast transients means those switching and lightning impulses. Okay, those are ultra fast. Second category is medium fast, which are basic power system faults categorized into unsymmetrical and symmetrical faults. Okay, and third category of fault, that is slow transient, is known as rotor dynamics, right? Third category of fault is rotor dynamics. Okay. So next two classes we will discuss how symmetrical fault is computed, which is mostly important for, sizing of the power, rating of the circuit breakers. Okay, how much current a circuit breaker at most will handle. That we can know only from symmetrical fault computation. Today we will discuss the Thevenin theorem method of computation manually. Next, lesson 21 will discuss how it is to be done systematically using Z-bus. Just like you have used Y-bus for load flow studies, similarly for fault computation we use Z-bus. In your power system lab, one code has been uploaded how to compute the Z-bus. There is an algorithm. Okay, so there is a simple algorithm. So you give the number of steps, it computes the Z-bus, and once you know the Z-bus, you can find out the fault at various points of the network. This is what they do industrially. Okay. So coming to what exactly is done in symmetrical fault computations, we will start with a revision of Thevenin theorem. So what is Thevenin theorem? Thevenin theorem. Shortcut, anyone can say? So we have a complicated circuit. We represent that by, yes, that circuit has certain characteristics, linear, etc. It doesn't matter. Mostly we consider linear. We approximate everything linear. So that complicated circuit we represent by means of an open circuit voltage in parallel with or in series with one resistance. Norton theorem is current source in parallel with resistance. Then how to compute this open circuit voltage? What you do is the point at which you want to know the Thevenin current. So across that point, what is the voltage happening? You do a network computation. So that is the open circuit voltage. And about the resistance, what you do or impedance, you simply sort the sources and compute the equivalent resistance. We'll see one example. That is what it says. A short circuit represents a structural network change equivalent to that caused by addition and of an impedance at the fault location. Now that impedance in a short circuit should ideally be zero. Right? It's short circuit, right? It should be zero resistance. But then we have certain fault impedance. Okay, or fault resistance. So it is equivalent to having a, suppose there is a fault at between these two points, one point and earth. So what is the current that is going to the earth? So that you can know only by finding the current in that particular path. So how to find that current? By getting the open circuit voltage across that point and finding out the network resistance, which is to be added with the short circuit resistance. Right? So it says in the next, this is from Elder book, but most easy definitions you can find in the network theory. The changes that take place in the network voltages and current due to the addition of the impedance between two network nodes are identical with. Okay. So here, this is the problem statement. So up to this is the problem statement. That means you have a fault between two nodes. What is the current? How to find out that? So then you need to understand that that is equivalent to voltage and current that would be caused by. So the voltage and current across that terminal will be those caused by an EMF placed in series with the impedance. That's what we discussed. EMF, equivalent EMF in series with the impedance. Having magnitude and polarity equal to the pre-fault voltage. So that open circuit voltage is actually the pre-fault voltage. Okay, that open circuit voltage is the pre-fault voltage, which is generally 1 per unit. And the and this voltage is that existed between the nodes in question and all other active sources being 0. That is, we sort all other active sources. So this is a complicated definition from Melgar book, but easier definition you can find in the network theory book, but its essence is the same. Okay, so see an example. So draw this circuit. Okay, first you draw this circuit. Draw this circuit. Okay. So what is the circuit? So you have a 100 volt applied, which is equivalent. Consider it to be the pre-fault voltage equivalent. And you have two resistances in parallel, 15 ohm, 5 ohm, and here 5 ohm and 15 ohm in this way. Whereas this is the fault location. This location is the fault location. We are interested in finding out the current in this path. Suppose, and you can consider this whole system to be a power system network. And these two are the points where the fault will occur. So our interest, what is our interest? Our interest is how much fault current will flow. Once we know how much fault current will flow, we can decide the rating of the circuit breaker. So to know how much fault current will flow here, that is simply IF is simply that IF, which is written here simply what is the open circuit voltage and what is the Thevenin resistance. Now what is the open circuit voltage across? That is what we need to find out, and the Thevenin resistance. It is easier to compute the Thevenin resistance first. Okay. So as you know, finding out the Thevenin resistance simply means sorting the sources. So we have sorted the sources, and this is our network. This network is essentially this network. Okay. This network is essentially, so you have got this 15 and 5 in parallel, this 15 and 5 in parallel. Okay. 15 5 in parallel, 15 5 in parallel. Always remember that this is where we need to compute the fault current. Okay. Right. So again, we will find out equivalent of this. What is the equivalent of this? 15 parallel 5. Again, 15 parallel 5. What is 15 parallel 5? 15 into 5 divided by 15 plus 5. Right? 75 divided by 20, which is 3.75. So 2 3.75 in series. Right? 2 3.75 in series. See, across this we are finding out, which is supposed to be the fault location. So when these two are in series, the final resistance is 7.5 ohm. Okay, so that is the Thevenin resistance. That is the Thevenin resistance across the faulted point. Across the faulted point. So this is what you have got. The difficult part is to find out the open circuit voltage. Now you know. So here E represents the generator voltage, 100%. But what is the voltage that is appearing at the fault point? That depends on the network topology. So topology here means the resistance 55, 55. Okay. So VAB, okay, we need to, what is VAB? What is the voltage across this point? That is, this VOC is basically VAB, right, across these 2 points A and B. But what is VAB? You know that VAB is equal to VA minus VB, right? Potential difference between the point is the difference of potential between the 2 points. So individually find out what is VA and what is B. Okay. Now what is VA? For that, assume this loop. Okay. Assume this loop. So if you assume this loop, what is the total resistance? See, when there is no fault, it is open circuit. When there is no fault, it is open circuit. It simply means 2 parallel branches. So what is the current through each parallel branches? Voltage divided by the total resistance. Here, I1. So I1 is 100 by 20. That is 5 ampere. So the current I1 here is 5 ampere. Now what is voltage VA here? So if 5 ampere is flowing through this, 5 into 5, 25 volt. So VA is 25 volt. Similarly, here the total impedance is 20 again. I2 is also 5 ampere, but this time VB will be 15 into 5, that is 75. So VA minus VB is equal to minus 50 volt. That means VAB is minus 50, or VBA is equal to 50 volt. Okay. So pre-fault voltage magnitude is equal to 50 volt. Okay. So voltage across this switch is 50 volt. So what is the fault current? What is this fault current? 50 divided by 7.5, because across this point the Thevenin equivalent is 7.5 ohm resistance, and the voltage that here is VA minus VB, which is equal to 50 volt minus 50, VA is 50, so 50 by 7.5. What is that? How much is this? Compute. 50 by 7.5, 6.67 ampere. So 6.67 ampere is the fault current. In which direction? B to A or A to B? B to A, because A to B is minus 50. Okay? Right? So this is exactly what we are going to apply to a power system network. We find out the Thevenin equivalent and then find out the current across the faulted terminal. Here exactly we are not finding out faulted terminal. What is the purpose of this whole study? Symmetric fault computation. The purpose is to find out the rating of the circuit breaker. How much current at most the circuit breaker will handle. Here we are estimating from the network topology. We are estimating the fault current. Okay. So now that you have seen a very simple network and application of the Thevenin theorem, you have revised the concept. We will apply the same concept to an actual power system, small network. Okay. Large network we use JBus. It is the topic of the next lesson. Okay. So we'll go to a actual network. This is again from the Albert book. Okay. So when we say short circuit analysis, what we mean? Do we mean unsymmetrical fault or symmetrical fault? When we say short circuit analysis, what do we understand? Is it for symmetrical fault or unsymmetrical? Symmetrical fault. When we do short circuit analysis, we are estimating the highest current that will be there in the fault, and hence we decide the rating of the various components like meter, circuit breaker, etc. Therefore, when we say short circuit analysis, this is basically three-phase symmetrical fault, okay, which is analyzed from a single phase. Symmetrical faults are balanced, so we can analyze that in a symmetrical basis. Draw this network. Okay, this is a simple power system network from the elder book. So draw this network. Okay. So coming to this network, you see that before we go for a fault analysis, we do load flow. Okay. We know the steady state situation of the network. So load flow is a prerequisite for fault study. So here for this network, a load flow has been already been made where everything is per unit, where the voltage at the two buses are computed. What is the load angle? You can know. What is the load angle in this case? Delta 1 to. What is the load angle in this case? Power transfers between 2 points, 2 nodes, based on is it voltage magnitude or the angle? Voltage magnitude difference है real power flow हो. Will real power flow occur only with voltage magnitude difference? This we discussed from the very beginning. No. Voltage magnitude difference only results in reactive power. For real power flow, we need angle difference. So here the load angle is 4.3, and this is why, because this corresponds to the corresponding rotor angle, rotor shift of these two generators. Okay, and rotor shift means real power input. Therefore, load angle refers to real power flow. Okay. And this is the power generated by generator 2. This is the power generated by generator 1. Here the magnitude of the power is same, but their angles are different. Okay. Now this is the power flow in this direction. This is the power flow in this direction, and we have got two loads. So here the load is a resistive load, which is 2 per unit here, and this is 0.8 per unit here. Okay, 2 per unit, 0.8 per unit. What is our purpose? Our purpose is to estimate the fault current at this location. Okay, and here the fault is not a solid fault. What is a solid fault? Solid fault means resistance is 0. In case of a solid fault, resistance is 0. Here the fault is occurring with a fault impedance known as ZL. Right? So how we proceed towards computing this fault current? Across this network we will find out Thevenin resistance and Thevenin voltage. Okay. So this is the explanation for what is obtained from the load flow and the description of the problem. You have got 3 MV, 3000 MVA generators and all this. This is done from load flow studies. Okay. And power at two load points, V square by R, because it is a resistive load. V square is 1 per unit divided by R is 2 per unit. V square is 1 per unit, resistance is 0.8 per unit. You see here 0.8 per unit, 2 per unit. So that is the load. Those are the loads. Okay. And here delta is 4.3 degree as we have computed. Now here comes the Thevenin equivalent. Okay. So what is the Thevenin equivalent? You represent the generators by their reactance diagram. So we represent the generators by their reactance diagram, and we have taken the subtransient reactance. Why? Why we took subtransient reactance, not transient or steady state? Because we want to know the maximum current, and subtransient reactance is the lowest, and the highest current occurs during the first peak, which is the subtransient reactance. So we do subtransient reactance. So it's the conclusion is that when you do short circuit studies, you take subtransient reactance of the alternator. But transformers, I have told you, those are not rotating machines, and hence they have the same reactance. Okay, steady state as well as they will fault. Okay, so this is the Thevenin equivalent. Then next step is computing right after application of the Thevenin theorem. After application of the Thevenin theorem, the network reduces to draw this circle. Okay. The steps in between I have not detailed step I have given in the slides. In the exam, if this question comes, you have to do the in between detailed steps also. Okay. But for now, you draw this only. Okay. Okay. So based on this, we know the pre-fault voltage. And the equivalent, this is the pre-fault voltage, this is the equivalent Thevenin impedance. We can find out the current. Okay, how it is computed? It is described here. Okay. This is that was for Thevenin impedance. This is for pre-fault voltage, which is 0.48 minus 90. It follows exactly the same approach as in that simple network. Okay, but it is more detailed. So finally, what is the utility? What is the utility of this short circuit studies? I have been telling you, this is for finding the rating of the circuit breakers. So we obtained in the end the Thevenin equivalent consisting of Thevenin EMF ET in series with Thevenin reactance HT, right? Ours was a simple system requiring a simple network reduction process. The same process can be repeated for a N-bus system, but we don't do in this manual way. We rather follow Z-bus system. So for a solid fault where ZF is 0, the fault current magnitude will be equal to simply ET by XT. Okay. Now write down this. The last line is very important and can be asked in a 2-mark question. What is known as short circuit capacity of a system? So the product of the pre-fault fault voltage and post-fault current is referred to as the short circuit capacity or fault level at the bus, given by ET into IA. Generally, do not consider the fault impedance because that will reduce this short circuit capacity. And in this example, the short circuit capacity is 6.94 per unit. That means 6 times, about 7 times more than normal current. Okay, which is about 21. The generator capacity was 300 MVA, so this is about 7 times that. 2100 MVA is the short circuit capacity. Okay, right? So this completes how to proceed with short circuit studies manually with Thevenin theorem. Next class we will focus how to do this systematically with Z-bus.